So hello students. In the previous class, we derived the stiffness matrix for 1D bar element both in terms of direct approach and minimum potential energy approach. And even we derived what is the strain matrix and what is stress matrix for 1D bar element. So from today's class onwards, we'll start with the problems. So this is the first problem on bars. Problem definition. For the bars shown below, determine nodal displacements, element stresses, and support reactions. Use elimination approach. So there are generally two methods of applying boundary conditions. So one is elimination approach, other is penalty approach. We have seen this approaches when we were discussing steps in FEM. In detail regarding this, we'll see it through a general problem. But now we'll use these approaches in order to solve the problems. Okay, you'll understand what is exactly is elimination approach, what is exactly is penalty approach. Okay, so in today's class we will solve this problem using elimination approach. So this is the problem given to you, a stepped bar. Okay, so this is the given data. Young's modulus E1 A1, Young's modulus E1 equal to 200 GPa, and cross section area of the first bar as 150 mm square. Then Young's modulus of the second bar. So this is made up of one material, this is made up of one material, and both are having different cross sections, and this is the force applied to it. And this direction x indicates. So with the help of this, as this is given to you, in that fashion we have to give the node numbers when we draw the FE model of the given bar. So first step is drawing the FE model. That is the first step, that is discretization. So in steps in FEM, what did we study? First is selecting the field variable. So what is the second step? Discretization. So we know what is the field variable here. So in this case, it's a structural problem. The field variable is displacement. Okay. So displacement we will be using u instead of u. We'll be using q here. So this is the FE model. So this bar is divided into one element and this bar is divided into one element. Okay, and node numbers are given here 1, 2 and 3. Why it is given, the node numbers are given from left to right is because here it is clearly mentioned the direction of x. Okay, here it's clearly mentioned the direction of x. Okay, and q1, q2 and q3 are your displacements at this point and this point. Okay, and there is a force F1 applied, which is given as 10 kilonewton and 5 kilonewton at node 3, and this is your length of the element, which is represented as Le1 for this one first bar and Le2 for the second bar, and this E1 and E2 are nothing but element numbers. So element numbers can be given in this fashion and written in bracket, drawn in circles, or you can write it like this as well. Okay, numbers you can give and you have to indicate that in a circle. This is how your element numbers are numbered. Okay, so this is the FE model for each and every problem. So a problem will be given to you. For that problem you have to draw the FE model. These are your 1D bar elements. 1D bar elements having single degree of freedom per node. So this is your first step for each and every problem. Either you take a problem on bar, you take a problem on trusses, or you take a problem on beam, or any problem. This is your first step. We'll be following the steps in FEM which we studied in the previous class. Okay, so this is your first step. The second step is determining the element stiffness matrix and element load vector or element displacement vector. So here in this case we'll find out what are the element stiffness matrices for the first element and for the second element. Since we have divided the given bar into two elements, we'll find out what is the stiffness matrix for element 1, what is the stiffness matrix for element 2. So we know what is the stiffness matrix for bar element, that is EA by LE 1 minus 1 minus 1 1. So here suffix E indicate element. Okay, so this indicates Young's modulus of this one, Young's modulus of this one, and so on for this as well. Okay, for each element. So first, as per the given data, substitute the values of E, A and LE. Substitute here and find out what is the element stiffness metric for the first element. So you will get K1 as 10 raised to 5, 6 minus 6, 6 and 6. Similarly, for the second element, make sure when you are writing the element stiffness matrices, whatever the common term which you get for both the stiffness matrices must be written outside the matrix. Okay, so it will be helpful for the next step. Now, the element stiffness matrix for second is 10 raised to 5 minus 1, sorry, 1.4 minus 1.4, 1.4 and 1.4. This is what you get. So why this 1, 2, 1, 2 is written here, 2, 3 here and 2, 3 here for element 1, 1, 2 for element 2, 2, 3. These are nothing but the node numbers for that particular element. Okay, these are nothing but the node numbers for that particular element. Element 1 belongs to node number 1 and 2, node number 1 and 2. So element 2 belongs to node number 2 and 3, 2 and 3. And these are nothing but, this is nothing but K11, K11. This is nothing but K22 value of the element 1. So this is K12, this is K22. Similarly for second element, this is K22, this is K32, so this is K23 and this is K33. Okay, so with the help of this numbers, okay, element numbers, node numbers will get the global stiffness matrix. That is your next step. Okay, so these are your element stiffness matrices for element 1 and for element 2. So once the element stiffness matrices are determined, next step is to determine the global stiffness matrix and write the global load vector as well as global displacement vector. Okay, so first we'll write the global stiffness matrix. So in order to find out global stiffness matrix, so whether it is 1, 2, 3, 4, so on, here there are two global stiffness, two element stiffness matrices. So K1 plus K2. In order to get the global stiffness matrix, you have to add K equal to K1 plus K2. Now, before you put anything here, first write down these numbers 1, 2 and 3, 1, 2 and 3. Since how many node numbers are there for the given bar? There are 3 nodes. Okay, so write down 1, 2, 3, 1, 2, 3 over here. So that with the help of element stiffness matrices, you can write this global stiffness matrix. So what is this K11 term from K1 element stiffness matrix? It is 6. Similarly here minus 6, minus 6. But what about here? So here with respect to the first element, it is 6. Okay, K22 value is 6. But with respect to the second element, there is one more K22 value, that is 1.4. So these two are added. Okay, so whichever the common element, when both the elements will get added over here. Okay, so since K22 is there with respect to the first element and with respect to the second element, those terms will get added here and that is written over here. Okay, written over here. And next remaining terms are written minus 1.4, minus 1.4 and 1.4. And all other values that is K13 and K31 will be 0. So this is your global stiffness matrix. This is your global stiffness matrix. Next, similarly, you write down what is the global force vector. So hence here there are only point loads on the given bar. Okay, no distributed load. Okay, so we will directly write this force. Okay, force on node 1 is nothing. There is no force on node 1, so 0. And what is the force on node 2? It is minus 10 e raised to 3. So here the unit is Newton. The unit is Newton. And y minus because the force is in opposite direction that of x, which is shown. And this is 5 into 10 raised to 3. and this is your global displacement vector, how it is written. Okay, since there are three nodes, Q1, Q2 and Q3. Okay. So this is our global stiffness matrix, global load vector and global displacement vector. This is your step 3. So once you write down this, once you get this global stiffness matrix, next step is to write the equilibrium equations. So we know the equilibrium equation is KQ equal to F. So write down these equations over here. So this is your right equilibrium equation. This is your equilibrium equation. Now, so once you write down the equilibrium equation, so next step is to apply the boundary conditions. So what are the boundary conditions given to you for the problem? So since the node 1 is fixed, since your node 1 is fixed, that is your displacement at node 1, that is q1 will be equal to 0. So in order to apply the elimination approach, okay, for the given boundary condition, that is for q1 equal to 0, eliminate first column and first row. If the third node is fixed, you will eliminate third row and third column. So since in this problem only first node is fixed, we will eliminate first row and first column. Okay. Now remaining matrix is written here as it is. Then these are the two equations which you got. That is 10 raised to 5 is common outside. 10 raised to 5 is common outside. And this is multiplied here. This row versus column. Okay. Similarly, row versus column here. You will get two equations. That is 10 e raised to 5 common 7.4 q2 minus 1.4 q3 equal to minus 10 raised to 3. Okay, 10 into 10 raised to 3. So here again second equation 10 e raised to 5 common minus 1.4 q2 plus 1.4 q3 equal to 5 into 10 raised to 3. So you will have these two equations, solve these two equations using your calculator. You can directly solve those two equations using the equation wherein you have to find out two unknowns. Okay, use that, you'll get what is the value of Q2 and what is the value of Q3. Write down all those displacements here. Okay, these are the displacements once you solve these two equations. That is Q2 will be equal to minus 8.33 10 raised to 3, 10 raised to minus 3, and Q3 is 27.38, 10 raised to minus 3 mm. So I'm using these displacements, we'll find out what is the element strain matrix, so element strains, and what are element stresses. So in the question, only element stresses are asked, but in the exam, you may be asked even to find out element strains as well. First, we'll find out element strains, then we'll multiply Young's modulus to that, you'll get what is element stresses. So in the previous class we have derived the element strain matrix and stress matrix. Okay, so this is your element strain matrix. So given by epsilon for the element equal to 1 upon Le minus 1 1. So this matrix, this one is called as was denoted by B, which is called as strain displacement matrix. So this is your strain matrix and this is your stress matrix. Just Young's modulus is multiplied to it, your Hooke's law, so you get what is stress. Now using this, you need to find out what is the strain in the first element, what is strain in the second element, and what is stress in the first element, what is stress in the second element. So with respect to the element 1, what are the nodes? 1 and 2. So you need to use your displacement q1 and q2. So substitute the values of displacements q1 q2 here, and this is 1 upon 50, the length of the element, minus 1 1. Solve this, multiply this with this, you will get the strain in the first element as 1.66 into 10 raised to minus 4. Similarly, you do it for the second one, second element. What are the node numbers for the second element? 2 and 3. So you need to use the displacements q2 and q3 here. So which you have determined in the previous slide. Okay, using our elimination approach boundary condition. So you'll get multiply this and this, you will get epsilon 2 equal to 7.142 into 10 raised to minus 4. Okay. Next, similarly, you just multiply Young's modulus for the given element. For the first one, it is 200 into 10 raised to 3. For second element, it is 70 10 raised to 3. 10 raised to 3. So you will get element stress for the first element as minus 33.32 megapascal, and for the second element as 49.99 megapascal. So this is how you find out element stresses and element strains, okay, for the given system. Next, what else is asked in the problem? We need to find out what is the reaction forces. What are the reaction forces? In order to find out reaction forces, we know the forces applied and the reaction forces. When you add both of them, the sum must be equal to 0. Okay. In order to find out the reaction forces, so this is the expression R equal to KQ minus F. So we know what is K, we know what is Q, we know what is F. We need to find out what is your reaction forces. So write down the expression for R1, R2 and R3. So since reaction will be there only at node 1. Why only at node 1? Because only node 1 is fixed. Node 2 and node 3 are, it is not constrained. So reactions at node 2 and node 3 will be 0. Now you need to only find out what the reaction at node 1. So you have the first equation here. Okay, the only unknown is R1. So multiply this first row with this displacement matrix and equate it to minus this force into 10. Don't forget about this, okay, because this is common for this matrix. So when you solve this, 10 raised to e 10 into e raised to 5, 6 into 0 will be 0, minus 6 into minus 8.33 into 10 raised to minus 3 minus 0. So when you solve that, you will get the reaction at first point equal to 4.998 kilonewton. So you know what are the forces applied. So it was minus 10 and it was plus 10 plus 5. So what is the overall force applied? It is minus 5. So what reaction are you getting? Plus 5. So when you add this and this, it is almost equal to 0. So it means your problem solved is correct. So these values are correct. Okay. So this is how you solve problems on bars. Not only bar problems, all the problems on FEM follow the same steps. So first you need to draw the FE model. Once you draw the FE model, you have to find the element stiffness matrices. Once you find out element stiffness matrices, you need to determine the global stiffness matrix. Not only global stiffness matrix, global force vector, and write down the global displacement vector. Then once you find out all those three, you need to write the equilibrium equations. Once you write down the equilibrium equation, you need to apply the boundary conditions. I've told you there are two methods of applying boundary conditions. So one is elimination approach, other is penalty approach. Okay, so for this problem we have used elimination approach. You know how elimination approach works. So for the given condition, for given boundary condition, that particular row and column will get eliminated. That's why the name elimination approach. So once we once we apply the boundary conditions using elimination approach, you write down the remaining equations. For the remaining equations, you find out the unknown displacements, unknown displacements. So using those unknown displacements, you find out what is element strains and stresses. Then once finding element stress and stresses is done, you'll find out what are the reaction forces.